A very good afternoon to all the dear children, officials, team members, principals, teachers. Welcome you all to the Junior Intermediate Chemistry webinar. I am Principal Ranjita Logishetty from TSMS Nedmanur, Nalgonda district. We are dealing in this chemistry session, that is the lesson 4, classification of elements and periodicity in properties. This is the session 4 dealt by our presenter, Dr. B.SAMPATH Kumar, PGT Chemistry from TSMS Shankarampet, Karimnagar district. Welcome, sir. Sir has already told you the insights of the periodic classification and this method where the elements are grouped on the basis of their characteristics. Welcome once again, sir. Now the session is all yours.
Thank you, madam. Thank you. Good afternoon, children. Today, we are going to deal with the chapter Classification of Elements and Periodicity in Properties, Intermediate First Year, Chemistry, Chapter 2, Session 4. This is Dr. B. Sampath Kumar, PGT Chemistry, TSMS Shankarapatam, Karimnagar District. My subject coordinator is Srimati Polu Sridevi ma'am, Principal, TSMS Pudur, Vikarabad District. Children, these are the topics we have discussed in the last session. Periodic trends in properties of elements, atomic radius. So in this atomic radius, we have discussed covalent radius, metallic radius, ionic radius, van der Waals radius. And next is lanthanide contraction, inert pair effect. So these are the topics we have discussed in the last session, children. Now this is the today's session overview. Ionization enthalpy, electron gain enthalpy, electronegativity, valency or oxidation states, anomalous properties of second period elements, periodic trends and chemical reactivity. So children, let us see one by one. The first one is ionization enthalpy. So here, what is ionization enthalpy? Let us see, children. The minimum amount of energy required to remove the loosely bound electron. What, children? The minimum amount of energy required to remove the loosely bound electron from an isolated gaseous atom to convert it into a gaseous ion is called ionization energy. See the children? Actually, this is the isolated gaseous atom. So from this, to remove this electron, valency electron, which is loosely bound, we have to supply some amount of energy. That energy is nothing but ionization enthalpy or ionization energy. So once again, I am reading, children. The minimum amount of energy required to remove the loosely bound electron from an isolated gaseous atom to convert it into a gaseous ion is called its ionization energy or ionization enthalpy. So this ionization enthalpy is about the removal of electron, children. The energy which is we are supplying, that energy utilizes to remove the electron from valency shell, which is loosely bound. Right, children? Now in this ionization energy, we have first ionization energy, second ionization energy, third ionization energy. So like that. So we will see here, if we remove the first electron, means from neutral atom, if we remove the first electron, that is called first ionization energy. Or if we remove the second electron from the outermost shell, that is called second ionization energy. So on and so forth, like that. Let us see. first ionization potential or first ionization energy. Here see children, what is the condition here? The atom should be isolated and gaseous state. Isolated means it should be single, should not be with contact with other elements, means not in bonding with other elements. It should be isolated and it should be in gaseous state, not in solid or liquid state or any other state. It should be, the condition is it should be in the gaseous state. Now see, here the element is isolated one and this is in gaseous state. So from this atom, if we want to remove an electron, this one, if we want to remove the electron, we have to supply some energy. So that energy is called ionization energy 1, because here we are removing the first electron from the atom. From the neutral atom, we are removing the first electron. That's why it is ionization energy 1 or IE1. After removing the electron from this neutral atom, the atom converts into gaseous state, of course, and a unipositive ion. Here, one electron is removed. That's why here 1 plus charge it get. So children, so after removing one electron from a neutral atom, we can get unipositive ion. So for that, we have to supply some energy. That energy is called IE1. This is the first ionization potential. In the same way, if we remove one more electron from this unipositive ion, that is the second ionization potential. Let us see. So dear children, here the second ionization potential is defined as, it is the energy required to remove the most loosely held electron from an isolated unipositive gaseous ion. So see here, unipositive. So already one electron is removed from neutral atom. That is the first ionization energy. And so that we can get the unipositive ion. And from that unipositive ion, if we remove one more electron, that is called the second ionization potential. See children here, this is the unipositive ion which is in the gaseous state. Of course, this is also isolated one. And from this ion, if we remove one more electron, this one more electron if we remove, we have to supply some energy, and that energy is called ionization energy 2 or IE2. So that here the unipositive ion loses one electron, so that's why it converted into dipositive ion. Here children, actually, why this after this element after losing one electron converted into unipositive ion? So this is very important. Why here +1 charge came? Because see here, this is the element. For example, let us assume sodium. This is the sodium element. What is the atomic number of sodium? Here the sodium atomic number is 11. That means 11 electrons and 11 protons are present in the sodium. From that atom, we removed one electron. Means how many electrons remain? Out of here 11 electrons and 11 protons, we removed one electron. Now how many electrons remain? Only 10 electrons. So 10 electrons, but 11 protons are there. Protons we have not removed. So here 10 electrons and 11 protons are there. Here one proton is excess. That's why here +1 charge. You know very well, the protons with positive charge and electrons with negative charge. So that's why here why one plus charges came? Because of one proton is excess in this particle. Here 11 electrons, 11 protons. That's why there is no charge. This is the neutral one. But here 10 electrons and 11 protons. Here one electron is removed. That's why here 10 electrons and 11 protons. So that's why one proton is extra. That's why here plus one charge. In the same way here, two protons are extra because already one electron is removed and again we are removing one more electron here. Two electrons are removed from this atom. Therefore here two positive charges are extra. That's why this is di-positive ion. In the same way, this is the third ionization potential. Now, what is the definition? It is the energy required to remove the most loosely held electron from an isolated di-positive gaseous ion. So this is important here. What is the difference for second ionization potential and third ionization potential? In second ionization potential, we are removing the electron from unipositive ion. In the third ionization potential, we are removing the electron from di-positive ion. That is the difference. So see here children, this is the di-positive ion which is isolated one and which is gaseous in state. From this we are removing here one more electron. So to remove this electron we have to supply some amount of energy. So that energy is called ionization energy 3 or IE3. After losing this di-positive ion, one more electron, it converts into tri-positive ion. So that we can remove the electrons and they get into the respected ions. See here. In general, the increasing trend in these values is ionization energy is always less than ionization energy 2, which is always less than ionization energy 3, and so on and so forth, children. So why this one? Why ionization energy is greater than ionization energy 1? So simply they ask children, why ionization energy 2 is greater than ionization energy 1? Let's see. Here, removing of electron from a charged ion is difficult compared to neutral atom. This is very important, children. Please try to understand why ionization energy 2 is greater than ionization energy 1. Because here in ionization energy 2, we are removing the electron from the unipositive ion. Here unipositive ion means, what does it mean? It is having one proton excess than the electrons. So that proton, which is we call effective nuclear charge, that effective nuclear charge is more on the valence electrons. That's why the valence electrons are attracted more towards the nucleus. Therefore, it is difficult to remove the valence electron. That's why here we have to supply more amount of energy than the first ionization energy. Why? Here this is number of protons and electrons are equal. That's why no charge. Here the nuclear attraction over valence electrons is 1:1 only. But in case of IE1, here the nuclear charge is greater than the electron charge. That's why more amount of energy we have to supply. So dear children, try to understand this one. So removing of electron from a charged ion is difficult compared to a neutral atom. Right. Now, what factors influencing ionization potential? Here children, ionization potential not only depends upon the atomic radius, it also depends upon so many factors. So what factors influence the ionization potential? Let us see. The first one is nuclear charge. Let us see. Here ionization potential is directly proportional to the nuclear charge. Means if nuclear charge is greater, then greater ionization potential it is having. That means, let us see here, for example, second period elements I have taken. Here, what are the second period elements? Lithium, beryllium, boron, carbon, nitrogen, oxygen, fluorine, and neon. These are having only two shells or orbits in their atoms. That's why these belongs to the second period elements. Right. So in this, the nuclear charge, let us see, lithium is having the nuclear charge. What is the nuclear charge here? The charge of protons. So how many protons lithium is having? 3 protons, because atomic number is nothing but protons number. Already we have learned in the first session. So here the atomic number of lithium is 3. That's why here the nuclear charge is 3. For beryllium 4, 5, 6, 7, 8, 9. For neon it is 10. So the nuclear charge for lithium is 3, for neon is 10. Right, here nuclear charge, actually what happens, see here, nuclear charge is increasing from left to right in a period. So when nuclear charge increases, the electron affinity value, see the electron affinity value of lithium I have given here, 5.39 electron volts per atom. And what is the electron ionization potential value for neon? This is 21.65 electron volts per atom. See here, the ionization potential of lithium is less than neon. Why? Because of the nuclear charge increased within the radius. So that's why here ionization potential is directly proportional to the nuclear charge. If the nuclear charge is greater, then ionization potential also high. Okay, children. Let us see the next one. Atomic radius. The ionization potential depends upon the atomic radius. It is inversely proportional to the atomic radius. Means if the atomic radius is more, the ionization potential is less. If atomic radius is less, the ionization potential is more. Why, children? Actually, what is ionization potential? Ionization potential is nothing but removing of electron from valence orbit. Here, when the atomic radius is more, the nuclear attraction decreases on valence electrons. Therefore, easily we can remove the valence electron. That's why minimum amount of energy requires. Therefore, if atomic radius is more, minimum amount of energy required, that is less ionization potential. If atomic radius is less, what happens? The nuclear attraction over valence electrons increases, and then it is difficult to remove the valence electron with the minimum amount of energy. That's why we have to supply more amount of energy. Therefore, ionization potential is high. If atomic radius is more, IP value is less. If atomic radius is less, IP value is more. Okay, children, right? The next one is screening effect. What is screening effect? See, the word itself, it is giving the screening. This is also called as shielding. Screening effect or shielding effect. What is the screening effect? Let us see, children, here actually I am telling, this is, let us assume this is an atom, and this is the positive charge species here located, which is called a nucleus, and these are the electrons, total electrons, and here what I have given some bracket here, these are inner electrons. What we call inner electrons or core electrons. These are also called as core electrons, right? And these are the valence electrons. Here actually in atom we can make 3 parts. One is the nucleus part, that is at the center of the atom. The second one is the inner electrons, and the third one is outer electrons or valency electrons. Now, if actually see here, these inner electrons, if the inner electrons are more and more, these inner electrons shield or cover or decrease or screen the attraction of nucleus over valency electrons. That is called screening effect. Here more inner electrons present, more screening effect. If less inner electrons present, less screening effect. For example, let us see helium. Helium is 1s2, means here actually helium is having only one orbit, only 2 electrons. So those 2 electrons comes under valence electrons. Means the nucleus attraction directly on the valence electrons, of course. But in these 2 electrons, the one electron, 1s1, here 1s2. 1s2 means here 2 electrons are there, but one electron is screening the nucleus attraction over the second electron. That's why here, because of these inner electrons, the actual attraction of nucleus over valence electrons decreases, which we call screening effect or shielding effect. So that's why here, see the children, ionization potential is inversely proportional to screening effect. That is, if the screening effect or inner electrons are greater, the ionization potential is less. If the screening effect or inner electrons are less, then ionization energy is more, because more attraction of a nucleus over valence electrons. Therefore, it is difficult to remove the valence electrons. That's why we have to supply more amount of energy. Okay, children, right? The next one is penetration ability. Penetration ability of orbitals influences the ionization potential. Let us see. Here, penetration describes the proximity to which an electron can approach to the nucleus. So, see children here, actually in an atom, electrons, protons, neutrons are there. Here, protons and neutrons are present in the nucleus. Here, because of the positive charge of protons, the electrons which are present around the nucleus, they are attracted towards the nucleus. Why they are attracted towards the nucleus? Yeah, because of opposite charges. Electrons are with negative charges and protons are with positive charge. Therefore, because of opposite charges, they attract each other. Here, protons having some mass, 1 unit mass each proton, but electrons are negligible mass, almost 1837 times of proton. So here electrons are almost no mass at all, but protons are having 1 unit mass, and these are present in the nucleus. So because of these opposite charges, here electrons attracted towards the nucleus. This is called the penetration power. Penetration means here the proximity to which an electron can approach to the nucleus, which we call penetration. Here, the ionization potential is directly proportional to the penetration ability. Let us see. Here, the penetration ability of s orbital is greater than the p orbital, which is greater than the d orbital, and which is greater than the f orbital. Why the penetration power of s orbital is greater, or s electrons is greater? Because we know very well, around this nucleus we have certain defined orbits are there, static orbits. So those orbits, in those orbits, in the first orbit s orbital is there, which we call 1s. In the second orbit, s orbital and p orbital is there, that is 2s and 2p. In the third one, 3s, 3p and 3d. In the fourth one, 4s, 4p, 4d and 4f. In among these 4 orbitals, which orbital is very closer to the nucleus? The s orbital. and the s electrons. So which are very close to the nucleus, they are very attracted towards the nucleus. So which we call the penetration ability. So that's why here s orbital is having more penetration ability than the p orbital, and so on and so forth. So if we want to remove the electrons from s orbital, it is difficult. That is, we have to supply more amount of energy, which we call the ionization potential, than the p orbital, and which is having more IP value than the d orbital, means d electrons. So like that. Okay, children. The next one is electronic configuration. So here ionization potential also depends upon the electronic configuration. Let us see. Ionization potential is directly proportional to the stable electronic configuration. What is stable electronic configuration? We know very well. We have, what is electronic configuration? Filling of orbitals with the electrons in the increasing order, of course. Okay, the filling of electrons in the orbitals in the increasing order of their energy is called electronic configuration. Now, what is stable electronic configuration? So those orbitals we know very well: s orbital, p orbital, d orbital, and f orbitals. And we also know very well each orbital accommodates actually only 2 electrons. Each orbital, whatever the orbital may be, s, p, d, or f, r, it accommodates only 1 or 2 electrons. But here, how many s orbitals? Only 1 s orbital. 1 s orbital maximum accommodates 2 electrons. So how many p orbitals we have? 3 p orbitals. That is px, py, pz. So those 3 p orbitals accommodates, each orbital accommodates 2 electrons. But here we have 3 p orbitals, therefore 3 into 2, totally 6 electrons it can accommodate maximum. In the same way, d orbitals. We have d orbitals, 5 d orbitals. What are those 5 d orbitals? dxy, dyz, dzx, dx square y square, and dz square. So we know very well. So totally 5 d orbitals are there. So each d orbital accommodates 2 electrons. Here 5 into 2, totally 10 maximum electrons it can accommodate. In the same way, f orbitals, totally 7 f orbitals are there. Of course, we don't know the exactly the structure of f orbitals. Here totally 7 f orbitals are there. Each f orbital accommodate 2 electrons. Here 7 into 2, totally 14 electrons maximum it can accommodate. Right. So here s orbital, only 1 s orbital. That's why here 2 electrons. If s1 is S1 electronic configuration, it is called as singly occupied or half filled. If it is in the form of S2, that is completely filled or full filled electronic configuration. Right. In the case of p orbital, the p orbitals are totally 3 p orbitals, and those 3 p orbitals are degenerate. So degenerate means they are having the same energy. So when they are having the same energy, we have to, if we fill the 3 electrons in each orbital 1, so we can get the p3 electronic configuration according to the Hund's rule of maximum multiplicity. We know very well. So while filling the electrons in the degenerate orbitals, first we have to, the electrons are singly occupied, and later they are paired up. So when the configuration is in P3, this is singly occupied electronic configuration, and this is the half filled one. This is the P6 is the completely filled one. In the same way here D5 half filled, D10 completely filled, and here F7 singly occupied, F14 completely filled electronic configuration. Right. So what here ionization potential is directly proportional to the electronic stable electronic configuration. What are the stable electronic configuration? Let us see here. Half filled or completely filled electronic configuration is more stable than others. So children, actually here this one, these are the half filled electronic configuration. So these are very stable, and these are the completely filled electronic configuration. These are also very stable. So other than this configuration, they are unstable. Means easily we can remove the electron. Let us see one example. Here, ionization potential of nitrogen is greater than oxygen. Actually, if we compare the ionization energy of this nitrogen and oxygen, first we have to see in which group or which period they belongs to. Or they belongs to the same period or same group, first we have to see. If we see that, then easily we can know the IP values. We know very well IP values, what happens in period and groups. Let us see. Here actually nitrogen is having the electronic configuration 1s2, 2s2, 2p3. These are the same period elements. See here, the last orbit is second orbit only. Therefore, these are the same period elements. But the valence electronic configuration is 2s2, 2p3. So in this last electron, that is the 2p3, these are singly occupied or half filled. That's why it is more stable compared to the here oxygen 2p4. This is not half filled or completely filled. Therefore, this is not stable electronic configuration. Therefore, less amount of energy is enough to remove this electron from oxygen. Therefore, oxygen is having less IP value than nitrogen. So actually, because of these are having belong to the same period, from left to right, the IP values increases. After nitrogen, the oxygen will come. That nitrogen is seventh element, oxygen is the eighth element. So actually the oxygen should have more IP value than the nitrogen. But here the controversy is there because of here electronic configuration. So we have to see the stable electronic configuration. It is directly proportional to the ionization potential. Right, children? I think you understood very well. Let us see the periodicity of ionization potential, means how it varies in a group and period. Here variation in a group. In a group from top to bottom, the ionization potential gradually decreases. What happens, children? Ionization potential in a group top to bottom decreases. Why? Because atomic radius increases in a group. When atomic radius increases, lost electron is loosely bound, means it is having the less attraction of nucleus. Therefore, easily we can remove the lost electron with the minimum amount of energy. That's why ionization energy gradually decreases in group. Next, in a period, let us see, in a period from left to right, ionization potential gradually increases. So what happens, children? Ionization potential increases because atomic radius decreases. See here, just now we have seen actually atomic radius of nitrogen is greater than the oxygen. Oxygen having the less atomic radius. It should have the more ionization potential, but here the ionization potential of nitrogen is greater than oxygen. This is because of electronic configuration. So here IP value not only depends upon the atomic radius, but also depends upon the other factors which we have discussed earlier. Okay, children, the highest ionization potential element in the periodic table is helium because it is uh, top of the periodic table, top right corner of the periodic table. It is having the least size. That's why it is highest ionization potential. And the lowest ionization potential element is cesium. Why? It is having the most size, and it is the bottom left of the periodic table. It is having the most size. That's why the IP values are less. So next, children, electron gain enthalpy. Okay, children. So what is electron gain enthalpy? The amount of energy released when an electron is added to a isolated gaseous atom to convert it into a negative ion. See children, here in the case of IP value, the amount of energy, this is the ionization, here electron gain enthalpy is completely reverse to the ionization enthalpy. Why? In ionization enthalpy, the amount of energy is required unknown, but here the amount of energy is released, and there the electron is removed from the atom, but here electron is added to the atom, and here the positive ion is formed after removing of electron, but here after adding the electron, negative ion is formed. See here once again, I am repeating children, the amount of energy released, not required. Okay, the amount of energy released when an electron is added, not removed. Okay, when an electron is added to a isolated gaseous atom to convert into a negative ion, not positive ion. Okay, this is completely reverse to the ionization enthalpy. Right, let us see here. The electron is adding to the isolated gaseous atom. Here the condition we have to maintain, isolated gaseous atom. So when the electron is added to the gaseous isolated atom, some amount of energy releases. So that energy, here see, here this is the isolated gaseous atom. Electron is adding to this atom. So when electron is added to this atom, that atom converted into this negative ion and some amount of energy released. This energy is called electron gain enthalpy or electron affinity. It is also called as electron affinity. See children, here periodicity of electron gain enthalpy means how it varies in a group and period. Let us see. Variation in a group. In a group from top to bottom, the electron affinity gradually decreases. Why electron affinity decreases? Atomic radius increases in a group. What happens if atomic radius increases in a group? See children, I will explain once again here. If atomic radius increases, this nuclear attraction decreases. If atomic radius decreases, the nuclear attraction is increases. See here, this is the less atomic radius, this is more atomic radius. Here if the electron is here, this is very near to the nucleus. But here, if the electron is here, it is more far away to the nucleus, therefore less attraction is there between positive nucleus and the negative electron. When electron is added fastly to the nucleus, then more amount of energy releases. That's why if the atomic radius increases, the IP value decreases, the EA value decreases. But here some exception is there children. Electron affinity of chlorine is greater than fluorine. Actually, the atomic radius of chlorine is greater than the fluorine. Fluorine is having less atomic radius. It should have the greater electron affinity. But why chlorine is having the greater electron affinity than fluorine? That is because of interelectronic repulsions between fluorine electrons and incoming electron. If the fluorine electrons are here, the incoming electron and fluorine electrons repulsions are there. Because of these electrons and these electrons both are having negative charge, some repulsions are there. So because of those interelectronic repulsions, the energy released is less. So in the case of chlorine, it is more energy. In the case of fluorine, less energy releases. So that is called here less ionization electron enthalpy or electron gain enthalpy or EA values for fluorine than chlorine. Very important, children. So many times in the various entrances, this is asked why here the electron gain enthalpy order is chlorine is having greater electron gain enthalpy or EA values than fluorine. Now variation in a period. How the EA values variation, let us see. In a period from left to right, electron gain and electron affinity gradually increases. Why atomic radius decreases in a period? See children here, from left to right in a period, atomic radius decreases. When atomic radius decreases, the electron is fastly attracted by this nucleus. Therefore, more amount of energy releases. That's why, so here more amount of energy releases, here less amount of energy releases. Therefore, in a period from left to right, the electron affinity increases. Right. The highest electron affinity element in the periodic table is chlorine. Actually, it should be fluorine, but because of interelectronic repulsions, here fluorine is having some less EA values than the chlorine. Now, the lowest electron affinity element in the periodic table is cesium because of large size. Next, children, electronegativity. So, what is electronegativity? See children, let us see the definition. The tendency of an atom to attract the shared electrons. Here we have to concentrate more, children. So dear children, here the attraction, the tendency of an atom to attract the shared electrons, not the singly electron. The shared electrons pair more towards itself in a heteronuclear diatomic molecule. In case of IP values or EA values, if the electron is removed, of course, the electron is added. But here, this is about the shared electrons. Means already this is which is participate in the chemical bond. So about that electron pair we are talking here. The tendency of an atom to attract the shared electron pair more towards itself is called its electronegativity. Let us see, for example, here A and B are chemically bonded. Actually, here A is having less electronegativity. Let us assume B is having more electronegativity. So here the tendency of this attraction of this paired electrons towards one atom. See here the electron density is towards one atom. This is called the electronegativity. The tendency of attracting the shared pair of electrons towards itself is called its electronegativity. Right. Electronegativity, how it varies in the group, how it varies in the period, let us see. In a group, from top to bottom, the electronegativity gradually decreases because atomic radius increases. When atomic radius increases, what happens? The nuclear attraction decreases, therefore, it not attracts fastly. That's why electronegativity means decreases. In a period from left to right, electronegativity gradually increases because atomic radius decreases. If atomic radius is less, then nuclear attraction is more, then strongly it attracts the shared pair of electrons towards itself. So children, here highest electronegative element in the periodic table is fluorine. Here electronegative element is fluorine. Electron affinity element is chlorine, but highest electronegative element is fluorine in the periodic table. The lowest electronegative element in the periodic table is cesium. So in the case of atomic radius, IP values, EA values, or electronegativity, in all these cases, the lowest value is cesium. But highest value is for atomic radius, it is the least atomic radius, that is the helium. Most atomic radius is cesium. In case of IP values, helium. In case of EA values, chlorine. In case of EN values, that is the electronegativity, fluorine. Right. Next, S character. Let us see what is S character here actually. S character means, see children, in hybrid orbitals, see these are the hybridization we discuss in the next chapter, in the future chapters, chemical bonding. Here hybridization sp, sp2, sp3 we know very well. As S character of hybrid orbitals increases, electronegativity increases. That is, see children, actually hybridization with the orbitals s and p, we have sp hybridization, sp2 hybridization, and sp3 hybridization. Here sp hybridization means here s 50% and p 50%. Here 50% s character, 50% p character. If it is sp2 hybridization, s character is 33.33% and p character is 66.66% because of two p orbitals are there. And here, if it is sp3 hybridization, s character is 25%, here p character is 75%. So just you see the s character, here 50%, here 33.33%, here 25%. So in which case the s character is more? In the sp hybridization, s character is more. So as the s character of hybrid orbitals increases, electronegativity increases. Means if we want to remove, or means the attraction of sp hybrid atom more attracts the electron pair, shared pair towards itself than the sp2 hybrid atom. And sp2 hybrid atom attracts the shared pair of electrons towards itself more than the sp3 hybrid atom. Okay, children. Next, we have say valency and oxidation states. This is very, very, very important, children. Once if we understand this valency and oxidation state, it is very easy to write the formulas. Let us see. So what is valency? Here valency is nothing but combining capacity with other elements. What is combining capacity? Means participate in the chemical reaction by losing or gaining or sharing of electrons. See here that this is the compound sodium hydride. This is the ionic compound. Here this sodium loses one electron, hydrogen gains one electron. Here the valency is combining capacity, means with how many elements sodium combined? Only one element. That's why here, this is the compound, this is the element, this is the valency. Here sodium valency is 1 because sodium loses only one electron. Here hydrogen valency is 1 because hydrogen combined with only one element, that is the sodium, or it received only one electron from the sodium. Or see here, this is the carbon dioxide molecule. This is the covalent molecule. So in this, the carbon valency is 4. How? See, let us see here, carbon is having 4 bonds around it. Means 4 electrons participated in the chemical bonding. So that's why here the valency is nothing but combining capacity with other elements. So here 4 electrons combined with other elements electrons. So this is called the valency of carbon 4, and this is the oxygen valency is 2. Why here? Only 2 electrons participated in the chemical reaction. So here HCN, hydrogen cyanide, here H, only 1 electron is participated in the with carbon, it is shared only 1 electron, that's why here 1 valency. For carbon 4 valency because here 1 bond, here 3 bonds, means here 1 electron, here 3 electrons. So totally 4 electrons participated. So in the same way nitrogen, here 3 because of 3 electrons participated in the chemical bond. So like that, the valency is nothing but the combining capacity with other elements. Right. The valency is determined by the number of electrons that an atom can lose, gain or share. See children, in the case of Here carbon dioxide and hydrogen cyanide, the electrons are shared. In the case of the sodium hydride, here electrons are transferred from one atom to another atom. Here the sodium is loses one electron and hydrogen gains one electron. Here variation in a group. How the valency variation in a group? Let us see. Valency not alters in a group from top to bottom. See children, actually same group elements having same valency. That means valency not alters from top to bottom. Next, in period, let us see, each period starts with 1 valency and increases up to 4. That is first group elements, 1 valency. Second group elements, 2 valency. Third group elements, 4 valency. Fifth group elements don't have the valency 5. They are having the valency 3. Here 3 and 5. Let's see. Let's see in the next slide. So here what happens? Each period starts with 1 and increases up to 4 with respect to the group number, and then decreases from 4 to 3, 3 to 2, and 2 to 1, 1 to 0. Let us see. How? Let us see, children. Actually, this is the first group elements, second group elements. So third, fourth, fifth. So like that. Here first group elements, all they should they are having 1 valence electron in its valence electron configuration, and this valence electron, this participate in the chemical bond. That's why the valency of this first group is 1. Second group, 2 electrons are having the valency orbit. Therefore, valency is 2. Here, valency is 3, valency 4, 5. So like that. So let us see next, oxidation state. The total number of electrons that an atom either gains or loses in order to form a chemical bond with another atom is called its oxidation state. What children here? The total number of electrons that an atom either gains or loses. This means the number of electrons gains or number of electrons loses by an atom is called its oxidation state. Actually, the oxidation state should be given with positive or negative signs, children. So let us say, for example, in hematite Fe2O3, ferric oxides chemical name, the oxidation number of the iron is +3 because here iron loses 3 electrons, and the oxidation state of oxygen is -2. Means here oxygen gains 2 electrons. Here actually iron, how many irons are there? 2 irons. So 2 irons, each iron loses 3 electrons. How many total electrons? Totally 6 electrons lost by this iron. How many electrons gained by the oxygen? Here 3 oxygens are there. Each oxygen gained 2 electrons. Totally 6 electrons. So here iron lost 6 electrons. Oxygen gains 6 electrons. But here the oxidation number is, for each iron is +3, for each oxygen is -2. Let us see, children, here. Here the valence and oxidation state I have given. So in group 1, there is a group here, numerical 1 or Roman 1A. Group 1, the number of valence electrons 1, valency 1, oxidation state is +1. Here see the difference between valency and oxidation state. Most of the students can get confused here. Valency and oxidation state, here valency is without signs, but oxidation state is with signs. And let us see how. Here for second group elements, number of valence electrons 2, valency 2, oxidation state is +2. So like that here, for third group 3, valency 3, and oxidation state is +3. For fourth group 4, valency 4, oxidation state is +4 or -4. Why this is +4 or -4? So up to fourth group, here this 1 electron is there actually for first group elements. If it want to get stability, it should have 8 electrons in its valency orbit. That is octet configuration. To get octet configuration, it should gain 7 electrons. So to get 7 electrons, it is difficult. So that's why it loses this 1 electron and gets the nearest noble gas configuration. Therefore, up to 1, 2, 3, 4 elements, they always try to lose the electrons. But here, fourth group elements, they lost the 4 electrons or gains of 4 electrons. So losing here, gaining. After losing 4 electrons, it get the octet configuration, or after gaining the 4 electrons, also it get the octet configuration. Here 50-50 there. That's why here +4 or -4. So next children, here the fifth group elements. Fifth group elements, here 5 valence electrons. These 5 valence electrons, actually to get the octet configuration, it should have only 3 electrons. Therefore, here these 5 electrons losing is difficult compared to the getting 3 electrons. Therefore, it tries to get the electrons 3. That's why here valency 3. Or if it want to lose, then it lost the 5 electrons, valency 5. Therefore, here the valency so varies from fifth group onwards. Let us see here fifth group elements valence is 3 and 5. Here 3 is by taking the electrons, or 5 is by losing the electrons. For sixth group elements, here the valency is 2 for gaining the electrons and 6 for losing the electrons. So in the same way, seventh group 1, 7. Here eighth group, no gaining of electrons, only losing of electrons, 8 electrons. That's why valency is 8. Oxidation state is +8. Next children, the last one is the anomalous properties of second period elements. So here second period elements shows the different properties compared to the other period elements. Let us see. Second period elements, lithium, beryllium, boron, carbon, nitrogen, oxygen, and fluorine, that differs in many respects from the other elements of their respective groups. Why? Let us see the anomalous properties. Actually, what are the anomalous properties shown by these elements? Let us see. Here lithium and beryllium form compounds with covalent character. Actually, children, here lithium, beryllium, they belong to the S block elements, and they are metals. They should form, they should lose the electrons. They should lose the electrons and they should form the ionic compounds. But instead of ionic compounds, they form covalent compounds. Means they participate in the chemical bonding by sharing of electrons compared to the losing of electrons. So this is the anomalous properties of lithium and beryllium. Next, the maximum covalency is 4 only. So actually, from top to bottom, if we observe here, for example, carbon, nitrogen, carbon, silicon, germanium, tin, lead, fourth group elements. Here carbon is maximum covalence is 4 only. But after carbon, silicon is there. Silicon, carbon, silicon, germanium, tin, lead, they show covalency greater than 4 because they are having the d orbitals and f orbitals. They are having the d orbitals. That's why their valency can increase. But these are having only s and p orbitals. Why the maximum valency covalency is 4? S and p orbitals only present. Here s orbital is 1, p orbital is 3. Totally 4 orbitals are there. That's why here the covalency is maximum 4 only for this. But the remaining elements of their respective group are having the d orbitals. That's why their valency can increase. Right. The next point is greater ability to form p pi multiple bonds. So children, these are the no other elements can form here p pi elements except these: carbon double bond, carbon triple bond, nitrogen double bond. Here this actually what is double bond here? Here one sigma bond, one pi bond. Here also one sigma bond, two pi bonds, one sigma bond, one pi bond. So like that, these elements only, the second period elements can show the multiple bonds. Here reasons for anomalous properties of second period elements. What are the reasons? One is small size, because top to bottom size increases. These are the second period elements, top elements. That's why these are having small sizes. Because of small size, they are having the some different properties than the others. Large charge by radius ratio. Because of here small size, okay, they are having large charge by radius ratio. High electronegativity because of small size. Having only 4 valency orbitals, 2s and 2p, just now I repeated. Next, let us see children, diagonal relationship. What is diagonal relationship? The elements of second period resembles the properties of third period elements. See children, diagonal relationship. So one of the anomalous properties of the second period elements. The elements of second period resembles the properties of third period elements. Present in the next group is called as diagonal relationship. See children here, if we see the lithium, we have to see the magnesium. Here, what is the definition? The second period elements resembles the properties of third period elements present in the next group. Means if we see the lithium, the third period and the next group, and means second group. So here for lithium, magnesium will come. For beryllium, aluminum will come. For boron, silicon will come. For carbon, phosphorus will come. So like that, here lithium and magnesium, beryllium and aluminum, boron and silicon, carbon and phosphorus, they show the similar properties which we call the diagonal relationship. So this is like diagonal. So that's why this is the diagonal relationship. So actually these are the page children, lithium, magnesium, beryllium, aluminum, boron, silicon, carbon and phosphorus. Here the atomic number difference is 9 children. For example, if anybody asks you, so which of the following elements is diagonally related to magnesium? If the options are like this, lithium, beryllium, boron, carbon. So here magnesium atomic number is 12. Just use subtract 9 number. 12 minus 9, how much? 3. So like that. Here aluminum is 13. 13 minus 9, 4. Here silicon is 14. 14 minus 9, 5. Here phosphorus 15. 15 minus 5. Here 40 means 6. So like that, we can get the here difference is 9 number. If lithium is asked, we should add the 9. 12 will come, means 3 plus 9, 12 will come. The 4 plus 9, 13. The 5 plus 9, 14. 6 plus 9, 15. So like that. So what are the reasons for this diagonal relationship? Due to the identical size of ions. Why these are having identical size? Let us see here. This, for example, let us see. Let us take the lithium. Lithium, if you come from lithium to sodium, the atomic radius increases because in a group top to bottom, the extra one more shell added. So that's why atomic number increases. But you come to the period from left to right. So one more here atomic radius decreases. So here if you come from lithium to sodium, atomic radius increases. And from sodium to magnesium, again atomic radius decreases. So that's why here lithium and magnesium are having almost similar sizes. So that's why they are showing the same properties. So due to similarity in the electronegativity. Next, due to similar polarizing power. So because of this, they are having the same chemical properties, which we call diagonal relationship. So periodic trends and chemical reactivity. This is the last one, children, in our session. So chemical reactivity is highest at the two extremes of a period and is lowest in the center. What, children, here? The chemical reactivity highest at the two extremes of a period. Means what is period? From left to right. Horizontally, if we go, that is called period. So from left to right, here left is, here two extremes, the reactivity is highest. Means at left and at right. Means S block and P block are having highest reactivity than the center, which is lowest in the center. Okay, children. So in the periodic table, the left side elements are having high reactivity and the right side elements are having high reactivity, but the middle element, which are called D block elements, these are having the low reactivity. S and P block elements are having high reactivity. Here D block elements are having the low reactivity. The reactivity on the left extreme of a period is because of having low ionization enthalpy. What, children? The reactivity on the left extreme of a period is because of having low ionization enthalpy. So actually, the left side elements low IP values. If we go along the period, means from left to right, the IP values decreases. So therefore, the left side elements are having more reactivity. Means easily we can remove the electron. So easily participate in the chemical bond. Right. Next, oxides of the left side elements are basic in nature. Why? Because here the left side elements are metals, children. So always the metal oxides are basic in nature. You remember this one. These are very, very fundamentals, very important. If you want to learn chemistry, good chemistry, you have to concentrate on the fundamentals. So here the oxides of the left side elements are generally metals. Here this is the general rule. The metal oxides are generally are basic in nature. And the right side elements are acidic. Here the right side elements are generally non-metals, children. Here non-metal oxides are always acidic in nature. And middle elements are amphoteric or neutral in nature. That is, uh, they are having the both natures, basic nature and acidic nature, or sometimes they are in neutral nature. So children, so in this session so far what we have learned, let us see: ionization enthalpy, electron gain enthalpy, electronegativity, valency, oxidation states, anomalous properties of second period elements, periodic trends and chemical reactivity. So children, this is the task for you. So I have given some multiple choice questions in this. So you please once again you listen the video and try to solve these questions. Here actually here up to 6 I have given the multiple choice questions, and the seventh question, from seventh onwards I have given the IPE questions. There is the long questions. This is the very, very, very important question in the IPE. Definitely they will ask in the IPE, children. So more concentrate this one. Define IE1 and IE2. Already in this session only we have learned IE1 and IE2. Why IE2 is greater than IE1? We have learned that one also. For a given atom, discuss the factors that influence IE. So already we have discussed, children. This is very important. You first try to learn this one in this chapter. This is for 8 marks. In the third bit you will ask. So that's why please concentrate and you learn this one. The next one is the write a note on S, P, D and F block elements. This is also very important. S block, P block, D block elements. Okay. So what are these periodic properties, how their reactivity, what are those general electronic configuration. So all those you have to learn write in this topic. Next, what is periodic property? How the following properties vary in a group and in a period. So already we have seen this. So ionization energy, electronegativity, electron affinity, atomic radius. So this atomic radius only yesterday we have discussed. The remaining in this session only we have discussed, children. So next, what are the salient features of long form of the periodic table? In the first session we have learned, children. So here up to seventh question, 8th question, 9th question, very, very important. And these are next. What is a lanthanide contraction? This is also important for 4 marks, children. Next, write the characteristic properties of D block elements. So very important, children, for 4 marks. This 11th and 12th question. Okay, children. Thank you. Thank you, madam.
Thank you, sir. Thank you, sir. I think with this you are going to end this chapter.
Yes, madam. Yes, yes.
Okay, okay. So all the fundamentals of chemistry were explained very well. And enthalpies, that enthalpy concept is very important for MSET, IIT, and G, as I know.
Yes.
And these concepts are beneficial to predict an element's properties, right, sir?
Yes, madam.
So definitely, students, please revisit this try to understand the characteristics of each and every element, the properties of elements, and important questions for IP also, like lanthanoid contraction and all. So every year we used to get such type of questions. So please do visit again and try to understand, copy down the notes. And thank you very much, sir, for the wonderful presentation.
Thank you,
Thank you.
madam. Thank you.
And we expect some more such interesting, good sessions from you, sir. Thank you.
Thank you, madam. Definitely, sure, madam.